Hello everyone, Assalamu alaikum. Welcome back to my channel. If you are new here, then please subscribe so that you can get more content like this. Now, in today's video, what we are going to do is we are diving into an incredibly important topic, which is lung cancer prediction using TensorFlow. With the power of AI and deep learning, we can create models that help in early detection, which can be life-saving. So, let's get started. Now, lung cancer is one of the most common and deadliest cancers worldwide. Early detection is crucial for improving survival rates, and that's where AI comes in. Today, we will build a model that can predict the presence of lung cancer from medical images. Now, we will be using a publicly available dataset of lung CT scans. This dataset contains labeled images indicating the presence or absence of cancerous nodules. It's essential to thoroughly explore and pre-process this data before feeding it to our model. Now, before moving forward, let's try to explore this dataset, what it contains and what type of data is included here. So this is the data. This dataset is comes from Iraq Oncology Teaching Hospital for cancer diseases. Now, lung cancer dataset was collected in this hospital over a period of 3 months. So it includes CT scans of patients, as you can see, the basic image. It includes the CT scans of patients diagnosed with lung cancer in different stages, as well as healthy subjects. So these were marked by oncologists and radiologists in these centers, and it contains a total of 1190 images representing CT scans, slices of 110 cases. Now, these are grouped into three classes: normal, benign, and malignant. So, out of these, 40 cases are diagnosed as malignant, and 15 are diagnosed with benign, and 55 are classified as normal cases. So, this is the whole theory behind these image data set, and images look like something like this. So, these are example images. So, it contains three folders. Uh, as you can see, benign cases, malignant cases, and normal cases. So there is no test and training split here, but we have to do it ourselves. So for that, I'm going to use a library um, for training and testing split. So let's get on with our coding part. Okay, so I'll be using Google Colab to run this application. You can use whichever platform that you are comfortable with. You can also run it on your local machine if you want to. So, if you're not familiar with Google Colab, how to use this, then the interface is quite straightforward. You have this code option where you can add this to add more lines of code, of course. Then you have this text option um, in which you can add headings like this or text that you want to write in between the lines. Then you have a very cool option of either selecting a CPU or a GPU environment. Just go to this change runtime type and you can select a GPU or a CPU, whichever you want to use. So I'm currently using a CPU to run my application, but you can of course select a GPU. So let's get on with the code. I've already prepared the notebook for you. I'll just go through this one by one so that you can understand how it's done. So firstly, we need to import some libraries. I'm importing a bunch load of libraries. The OS, NumPy, Plotly, Matplotlib, TensorFlow. Will be my main library to use for images, for detecting uh, the cancerous nodules in the images. And then I'm also using sklearn for train test split and classification and accuracy as well. Now, first things first, I need to select a database. So for a particular database, what I need to do is I need to have it available at my hand. So in this case, what I'm doing is I'm not uploading it directly on Google Colab. What I'm doing is I'm connecting my Google Colab to the database directory that I am using, which is Kaggle. So how to do that? Let me show you. Firstly, what you need to do is write this command that will connect your Kaggle database to your Google Colab OS environment, and after this you have to put this link of this folder in which you want to copy your content or your database. So how to get this link? What you need to do is simply go to this option, which is the list of folders that are available to you, that are accessible by you. So click on any folder and you can copy this path like so. And what I need to do is paste this path here. Okay, but I don't want to put my database directly in the sample data folder, so I just need it here, so I'll just do this. Okay, after this, let me just run these commands as well. So after this, what I need to do is I run this command. When I run this command, it will connect my Google Colab to the Kaggle database that I want to connect. So of course I have to give an API command afterwards as well. I'll show you. Now, after this, what I need is to go to the Kaggle database that I want to use. This is the database that I want to use. So uh, how to connect this one to my Google Colab is simply by accessing this option and copying this command, copy API command, and that's it. You don't have to do anything else. So once you have copied this one, you just need to paste it here in the command code section and add an exclamation mark so that it knows that it's a runtime command, and once you run this, your database will be downloaded like so. So I've already downloaded my database, so that's why I'm not running this again. So this is present here in the zip format, as you can see. Now next thing I need to do is unzip this data that I have copied from Kaggle. For that, I just need to write exclamation mark, unzip, and space, and link of the folder that I want to unzip. So for copying that link, you just need to go to this option, copy this path, and paste it here. Okay, and then write space and -t, and then space again, and in the next section. And after that, what you need to add is the link of the folder that you need to copy it into. So I'm just copying this unzipped content into this folder. So that's it. Once this unzipping is completed, you will see your data inside this folder like so. So I have the three cases: benign, malignant, and normal, as I showed you previously. Now everything is set. Just need to pre-process the data that I have collected. For pre-processing, what I am doing is just running the images through the directory, providing the path, and I'm converting them into grayscale, and then what I'm doing is resizing them into 128 by 128. Now this is a crucial part because you have to get your images to the same format. So in this case, I'm converting them to 128 by 128 pixels. The reason being that the convolutional model that I'm using requires an input image size of 128 by 128. I'm setting this standard, but you can set your own standard as well. And you can see the standards of the predefined models or pre-trained models that are available in different libraries. So I'm not using any pre-trained model. I'm making my own model using TensorFlow. Now the next thing I'm going to do is assign numeric labels to classes. So what I'm doing is assigning each class a numeric label, because that will be really helpful or easy for our model to predict a label in the form of numeric digits. So I'm assigning a label 0 for benign class, and 1 for malignant class, and label 2 for normal class. I have these three classes. Then I'm just counting the images and labels and putting them in arrays. The next important thing is to perform the train test split. So I'll be using this train test split method that I called earlier, as you recall this, from this sklearn library. So I'll be performing this one, and I've set the size of the test set to 20%. That means for training I have 80% of the data. Now after this train test split is performed, what I am doing is defining the categories to their corresponding image paths, creating a dictionary. Then I'm iterating over the categories, loading images from the directory, and then creating a subplot. So in short, what I'm doing here is just making sure that I have the appropriate data set. That's it. Let's just see some random images from the model random images from the data set that we just extracted from Kaggle. So yes, I have required images now. Now, the next important step is to create my model. In this model, I'll be using a variety of convolution layers, and I'll be performing max pooling and also some dropout, just to make sure that my model doesn't overfit. Now, here is my model's summary that I implemented. Let's see how this model is. So this model has 3 convolution layers, okay, and max pooling in each layer after each convolution layer, then dense layer, 2 dense layers, and in between the dense layer there's a dropout as well. So there are total of this much parameters, as you can see, and these are the training parameters as well. So this is my complete model that I implemented for this for training on this data set. Now, this training can take some time depending on your hardware, but it's crucial to ensure that the model generalizes well on unseen data. Okay, so let's try to train the model. Now, this will take time, as I said earlier. So once it gets completed, I'll get back to you. Now you can see that I am using this compile method, and in that I'm using Adam optimizer. You can use different optimizer as well, depending on whatever you are planning to do, but for this particular application I chose Adam, and I chose categorical cross entropy loss for this one, and I'm going to evaluate on accuracy. So you can also put on different metrics, evaluation metrics, and try to figure out which model parameters are best suited for your data type. Okay, now you can see that my um, model has completed training. So before going to training, I forgot to talk about the number of epochs and batch size and validation split, etc. So we talked about training and test split, but we didn't talk about validation split. So this is also to ensure that our model fits perfectly. Then there is this batch size. I'm giving this a batch size of 32. So and the number of epochs are set to 10 here, but you can increase or decrease based on your model. Now for this data set, I thought that 10 was quite enough for number of epochs for training my model to get the appropriate results, but you can play around with this and get a better result as well. Now let's see how our model has trained. You can see that in the first epoch loss is quite high and accuracy is quite low, but as we go down to the number of epochs, the loss starts to decrease considerably, and then the accuracy is starting to increase as well. Okay, so it goes to this 0.05, which is quite good, and my accuracy of the model becomes 98%, which is quite a good accuracy for this deep learning model. And similarly for validation set, the accuracy is increasing as we go down the epochs, and validation loss is also decreasing. Now let's plot this so to get a visual idea of how our model looks like. Now this is the blue one is the training accuracy, and red one is the validation accuracy. So as you can see that the training accuracy is quite smooth, but validation one goes up and then down and then up again. So there's this happening here. So I think this in this part it's overfitting. That's why it's doing that, a little bit of overfitting. Then the loss, if we plot the loss, blue one is the training loss and red one is the validation loss, and it seems quite good. Now let's move on to the test part. So because I have three classes, so I have stated this as number of classes as 3. My test loss is comes out to be, with the parameters that I have trained my model on, the loss comes out to be this one, 0.06, and the test accuracy is quite good, 98%, which is quite close to the accuracy that I got on training set. So that means my model has converged, and my model is quite good at predicting whether the given CT scan is of cancerous nodule, or is it a normal or healthy person's CT scan. Now let's test it on a single image. Now what you can do is what I have done here is set the path, check the path. You can check the path here directly from this data set that you unzipped. So in that folder I had three different folders: benign cases, malignant cases, and normal cases. What I have taken right now is the normal case patient, taken any image, takes some time to load. So you can take any image, just copy this path and provide it here, and that's it. Then what I am doing is pre-processing the image, and in that pre-processing I need to set this size of the image to 128 by 128 because I have prepared my model accordingly. So if you don't do that, and if you give raw image to your model, then it will not predict correctly, or it might not work as well. So you have to set this standard here. And also, because I was in pre-processing, I was converting my images to grayscale, so here I have to convert it to grayscale as well. Then this is just pre-processing, and then I'm applying my model and predicting whether it is a normal or healthy patient's image, or a malignant or benign or a cancerous patient's image. So in this case, because I took the image from the normal, so it should predict normal, and it is predicting a normal image, a normal patient's image. Let's take another case. Let's take an image of a malignant case and predict whether our model and check whether our model predicts it as a malignant or not. Now I can take an image, so I'm just copying this path and providing this path here. Okay, so now I have this. I have to run this again, load the image, pre-process it. I think my internet connection is quite slow right now. That's why it's taking so much time. Otherwise, it doesn't take that much time. Now, let's see if this predicts correctly. And yes, it did predict that it was a malignant case. So there you have it. This was all the coding that was required for this overall lung cancer prediction project. That's it for today's video. As you have seen, we have built a deep learning model for lung cancer prediction using TensorFlow, which could be a step forward towards the more advanced medical AI applications. If you found this video helpful, don't forget to like, share, and subscribe for more tech tutorials. Also, leave a comment below if you have any questions or suggestions for future videos.